You are currently the only person in this conference.
Okay, so today will be a smaller lecture. I'll only cover one topic, which is principal component analysis. Tomorrow we'll cover LDA, and that will be the end of the course. So before I begin, I might want to just take a step back, and I know you guys have been studying. It's not very long since the exam is now there, so please let me know if you have any doubts regarding the things that were discussed earlier, or anything that you want, any topic you want me to discuss tomorrow in the class, so that we can take that forward and prioritize it more, right? So I'll give you a minute to think and try to answer if you have any questions. If you don't, then we'll start the lecture today. Okay. Okay, let's start. Wait a second, I didn't upload the PPT, is it? Okay. Give me a minute, sorry. Okay, sorry. Yeah, sorry for the delay. Okay. Hmm. Okay, so let's start talking about dimensionality reduction, right? So, dimensionality reduction is one of the important topics of your exam. We'll again start with talking a bit about dimensionality reduction, and then we'll solve few questions given in the exam last year and before. Today's class requires some background. You need to know a bit about statistics and geometry. So, if you know that, it's good. If you don't, then you may have to watch this lecture again to after you come back, reading those about those other topics as well. Okay. So, dimensionality reduction, and as I said before I start, it will be a short lecture because it's only one topic that I have planned to teach today. Principal component analysis. It won't take much long. I will also give you a shortcut if you are not able to understand some things. Then There's a shortcut as well where you can, if you know this much only, that's enough, right? So that's what it is. So I'll also give you the shortcut, but the plan is to cover this in a more greater depth. So yeah, so dimensionality reduction is a very important, sorry, to silence. So yeah, so dimensionality reduction is a very important technique in your machine learning. And what it does is if you have a data set, let's take any data set, capital D, okay. This data set has n points and let's say it has m features. So to give you an example, let's say if I have a house pricing data set, let's say I have a house pricing data set D. Now, let's say the house has maybe the number of square feet, the number of bedrooms, let's say the number of rooms, actual number of, sorry, let's say if it is in a society or it is independent, right? And what is the price of the house? So you might have one house which is like 900 square feet, it has two bedrooms, it is in a society, and its price is, let's say, 1 CR, 1 crore. Let's say you have a house 1200 square feet, it has three bedrooms, it does not belong to the society, it is also 1 CR. Let's say you have a house with 1300 square feet, let's say three bedrooms, it is in a society, this is 2 CR. Okay, so typically these rows are your different points. Okay, and in this case, n is 3. While the columns in the data set, which is the square feet, the bedrooms, the society, the price, are the different features in the data set. So in this example, m is equal to 3. Okay, so this is basically what the data set kind of means. So now what we want to do here is that let's say that somehow my manager, let's say at my data science company I work at, he's not happy with having 4 features. Okay, he says it takes a lot of time to build the model. It takes, why are you taking 4 features? Can we reduce it, right? So you might want to have from m features, you might want to have a subset of m features, let's call it m prime, where m prime is a subset of n. Okay, basically you're trying to reduce the dimensionality of the data. You're trying to reduce the data from 4 features to, let's say, 2 features. Okay, this is called dimensionality reduction. Okay, why do we do that? I'll give you 2 examples. And why are even we talking about why we do it? Because, why is it such a big problem? Because you might think that there are m features, like there are 4 features here. Sorry, it's not 3, it's 4. Value of m is not 3, it is 4. I'll just correct it. M is 4. Okay. So there are 4 features. You might take 2 of them. You try with every 2 features. You build a model, um, and then you try to see whichever gives the best performance. You will say, I will take those 2 features. That is a good way to do it. That is the most exhaustive way of doing it. Now, what is 4C2? 4C2 is 6, right? 4C2 is 6. So there will be 6 different models you make, and that way you can actually do this problem. This problem is solved then, right? But the problem is common data sets do not have 4 features only. Let's say if a data set has 1,000 features, right? and I want you to select two of them. So will you actually go ahead and make models for all of them? Maybe not. It's like 4,990 different variations of two features, and you make these many models and compare them. It's a pain, right? So can we do things statistically? Can we try to do things more in a structured statistics manner rather than doing brute force? Is what is the idea of dimensionality reduction. Okay, now why do we do dimensionality reduction? There are primarily two reasons. Okay, how we do it? This is the brute force method, and what is the other method? That is only the part of the lecture. We'll look at that today. Okay, so there is a brute force method of doing things. You can just do anything, whatever you want. Like you just take two features. Let's say if you want, so this two can be three also, right? I'm just taking example as two. It could be three as well. So you might take two features, three features, whatever you do. So this is a brute force method. How do we do PCA is what the topic of the lecture is today. Okay, now why do we do dimensional reduction? There are primarily two reasons. Okay, one is simplification. You want, as I said, your manager said that, boss, I'm not happy with four features. Can you simplify it for me? Can you just have two features? Because one of the benefits of having lesser features is if you have, let's say, only one feature. Okay, let's say you have only one feature, which is X and Y. You can actually plot it in the graph and see you can plot it in the graph and apply intuition from it. Let's say there are two features, still you can do so. X1, X2, and Y. If you have two features, still you can do. You can plot a graph and try to visualize the model. Now, this could be one of the reasons why simplification might be required. So it becomes easier to interpret. And also lesser features means lesser compute. You have lesser things to compute. You have lesser the features to have that you have to compute. So easier to interpret and compute. And the second most important reason why we do PCA is, again, I expect some background in machine learning to answer this, is to reduce overfitting. So overfitting is one of the um, very very big problems in machine learning. So if you want to reduce overfitting, one of the ways is to do dimensionality reduction. Okay, now what is overfitting? I have talked about it for 2 hours in one of the lectures. Please look into that lecture. It's called bias variance trade-off. So to remove overfitting, you try and use this dimensionality reduction. Okay. Okay. Oh, Mohammed, you joined, is it? Okay. I thought no one will join. So yeah. Okay. Hi, Mohammed. Good afternoon. Good afternoon. How's your preparation going on? Going on? Okay, no problem, no problem. Okay, you are Gate DA or Gate CS, Gate DA both? I think you're CS as well. Yeah, you were in one of my compiler design lectures as well. Sorry, I shouldn't have asked that. Anyway, okay, okay. So I expect some background here in knowledge here for this topic when I start talking about PCA. So if you find things written in Hebrew, Latin, I'll give you some references of which lectures you have to watch. You can watch that and come back, and then you will be able to better understand things. Okay. For now, I think it should be clear dimensionality reduction, how it does and how it works. These are just basic theory. Till the point I start talking about PCA ka math, then things will actually go a bit more difficult. Okay. Chalo. Let's talk about the techniques to do dimensionality reduction. Uh, okay. So let's say you're trying to do machine learning, okay, and let's say I ask you to make a model. Let's say the data is like this, okay, and let's say if you can answer this question. So there are two features, X and Y, okay. And let's say the value of x is 1. For that, the value of y is 2. For the value of x being 2, value of y is 4. For the value of x is 3, value of y is 6. For the value of x 4, value is 8. For the value of x as 5, the y value is 10. For the value of x as 6, the y value is 12. Okay. Can you tell me if the value of x is 7, what can you predict a value for y? What is the value of y if the value of x is 7? Can you do prediction? Can you predict what could be the value? For 1 it is 2, for 2 it is 4, for 3 it is 6, for 4 it is 8, 5 it is 10, 6 is 12, 7 will be? It could be anything, but by looking at the pattern, do you see a pattern here? 14, right? Yeah, perfect, 14. So it could be anything, but looks like it's 14. Most likely it's 14 because that's what I can see, right? So have you done machine learning? Quite yes, because we can make a model now. The model is y equal to 2x. Model is nothing but just a function. So it's y equal to 2x, the model. Whatever the value of x you plug in, you get value as 2 times that, right? So machine learning is done, but still, okay. Now what I will do is, I want to strengthen my belief. Okay, I want to strengthen my belief that indeed this relation is true. So what I will try to do is, I will try to add a new feature, because maybe just having x you are not maybe very confident that this is the answer, because it could be any value. So let's add one more feature. Okay, let's say this is another feature x prime. The values are like this: 1, 4, 9, 16, 20. Oh, sorry. 1, uh, sorry, what should I do? Yeah, 2, uh, sorry. Okay, so this x prime is 3, 6, 9, 12, 15, 18, 21. Now, can you tell me if there is a relation between x and x prime? Correct. So x prime is 3 times x. Agree? Agree? X prime is 3 times x. With 1 unit of x increase, x prime increases by 3 units. In terms of statistics, it is called correlation. X and x prime are highly correlated variables. It is like, even if you do not have this feature, you are not losing out on anything, because this feature x prime was just derivable by x. You can use the feature x to derive the value of x prime. It is like saying I added a new column and wrote 3x here. Why do you want to do that? I may add another column 4x. I may add another column 5x. I may add another column 6x. So you may want to even remove this and have only one feature. So this is one of the dimensionality reduction techniques called correlation elimination. And this is one of the very famous techniques in your machine learning literature today. Many companies use this. Even I personally had implemented a framework that kind of had done this, which is to check the correlation of different features. And if the correlation is above some threshold, delete one of the features, because if they are two features are too correlated, then they are not. You can have only one. You need not have both the features. So one of the methods of using dimensionality reduction is to do something called feature selection. You select the features according to some criteria, and one of the methods is remove by collinearity. Correlation, sorry. Correlation elimination, few people call it remove by correlation. Idea is the same. Okay. Another method is, for example, there are two features and you want to select only one. You might train a model, one model each, and see whichever is giving better performance. You take that method. So by building predictive models. Okay. And the second method, this is to select features. Now, other way is, can we try to transform the features into a new set of features? It might not make sense now, but please hold on for some time. It will make sense in some more time. So it's called something called feature extraction. Okay, and one of the most important feature extraction techniques is called principal component analysis, PCA, and LDA, linear discriminant analysis. Now, PCA is an unsupervised learning problem. You do not have the labels. So it's like feature elimination without considering labels. And LDA is also feature reduction, dimensionality reduction, feature extraction, but it is a supervised learning problem where you introduce the labels back into the game. Okay, LDA is a topic that I want to cover tomorrow. It's a very, very difficult topic and it requires a lot of background in stats, machine learning before. I'll give you what you have to study. So that's LDA for tomorrow. Today we look at PCA. Yeah, tomorrow morning we have a class 10 to 12. We'll look at LDA and I'll give you some derivations. Okay. I do not want to. The LDA requires two lectures actually, to be honest, because it's very big topic, but I'll try to condense them as much as possible and give you some references. So that's about LDA. And today we will try to look at PCA. Okay. Now, right. So this is about dimensionality reduction. Basically, the idea should be clear by now. We try to reduce the number of features in the data set from M to M prime. And why do we do that is we do it because we want to simplify the model to make it easier to interpret and compute. And the second most important thing is we might want to reduce overfitting. Different ways of doing dimensional reduction. One is feature selection. You may remove by correlation. You may build predictive models and find out which features you want to select. And you might do something called feature extraction. You extract features from the given set of features. It might sound like I'm creating more features, but no, it will make sense in some time, just run for some time. Now, in the unsupervised world where there are no labels, it's principal component analysis. In the supervised world, where there are labels, it is linear discriminant analysis. So this is about dimensionality reduction in brief. Now let's start with PCA, principal component analysis. Okay. Now, principal component analysis requires some background or knowledge on something called eigenvalue and eigenvector. Okay, if you know a matrix, how to find its eigenvalue and eigenvector is what is expected. Okay, okay, okay. Let's start with PCA. Okay, and since we are learning in a whiteboard, there's no 3D, there's no 4D, 5D dimensions that can be visualized. So all the examples I take will be of 2D data. Okay, so let's start with PCA. So PCA or principal component analysis, principal component analysis, abbreviated PCA. Okay, and if you find it's lot of math heavy, you can tell me. Okay, I will try to tone down a bit. This is only the second time gate DA has been there in your system, so still it's very unclear what type of questions are asked from this topic. Yes, last year's gate DA there was no question from the math part of PCA. There was more on the conceptual part, which I've already covered. Okay, but you don't know this year what happens. This year they might ask. Again, don't worry if you don't understand the math. It took a lot of time to me as well to understand these things. Just listen to it, or maybe just listen to it, just hold on for some time, just hear me out, and then later on you may want to revisit it again to understand it more. Okay, so let's start with PCA. Basically the idea is to, again, as I said, always this thing should be remembered. Okay, we are always wanting to do something called dimensionality reduction. Why do we do it? To simplify the model, to reduce overfitting. Okay, so this is the main funda, this is the basic funda why we are doing all these things. So let's start with PCA. Okay, you are not in DA. Are you not giving it DA? Then I don't know why you are in this class, because it's a gate DA topic. I mean, if you're interested to learn machine learning, sure, but yeah, it's a gate DA topic, so it's machine learning topic. Yeah. Oh, admit card is only CS. Oh, you appeared. You want to appear for DA. You're saying, and you may have filled the form for DA as well. Oh, so they do not give you two admit cards or just one? I don't know how it works, because in my time it was no gate DA. So oh, only one, and they have not mentioned DA there. That is very, very strange. Did you check with any of your friends if they are also have the same problem? Okay, I will suggest one thing. Maybe if you want, you can put a message in this the group. Okay, we have a group. I think you have access of it, WhatsApp group, because there are many other students who are also appearing for CS and DA both. They might be able to answer it, right? Why? Maybe there are two admit cards. Maybe there's just one admit card. So when is Gate DA, by the way? The date? Gate.iit Roorkee, right? IIT Roorkee is organizing the gate. So when is Gate DA? Which date? Examination schedule. Oh, Gate DA is on 15th Feb, while Gate CS is on 1st Feb. Okay, okay. 1st Feb and 15th Feb. Yeah, I kind of think Gate, there will be two admit cards because there are two different exams. I think so, but I will suggest just put a message in the group so that someone is there can help you out. Okay? Okay. Okay. One second. I'll be back. Yeah. So I'm back. I'll suggest again put a message in the group. Someone will definitely help you. Right? Okay. Anyways. Okay. Right. Okay. Okay. So let's start with principal component analysis. And again, as I said, I'll look at a two-dimensional data set. So let's just first look at the data set. So let's just take an example data set. Okay, I'll just draw a data set on the Cartesian plane. Okay. This data, as I said, has two features. There is no labels because we are in the unsupervised learning world. Okay, so this data set has two features. Um, and the data is like this. Yeah, just giving an example data set. Okay, it could be anything. Just and data is not as perfect as I'm drawing in a straight line, but to explain you things, maybe it's beneficial. Okay, so okay, so this is the data set, right? And and right. So now once you know this data set has variance, right? Variance measures the variability of the data. So let me give you some notation. So this data set X, it's an n by 2 data set where n is the number of training examples, 2 is the number of features, right? And this is the values. So x11, x12, x21, x22, so on and so forth, xn1, xn2. Okay, this is the data set capital X. Now there is something called the covariance matrix you might have studied in your stats. It measures the variability across different dimensions. Okay, and covariance of X is a matrix again. The first element is the covariance variance in X1. This element is a variance in X2, while S12 measures the variance across the two features. This is the covariance. And also just to give you, just to write it here, there's also correlation matrix, which measures how two or more features are related, how two or more features are, sorry, how they are related to each other, right? And for that, we have um, the correlation between a feature with itself is 1, right? Correlation with a feature with itself is 1. This is R12, this is R21. Okay, these are just some terms I'm throwing at you. Okay, and covariance matrix measures the variability. Okay, and by the looks of it, just giving you a ballpark number, the correlation between x1 and x2 here is about zero point 0.9 because it's highly correlated, as you can see, right? And so the correlation between 2 1 will be, any guesses, is actually negative of 0.9 because one is reducing and one is increasing, right? You can see that way. Okay, if it doesn't make sense, again, don't worry about it. Just giving you some ballpark numbers just to give it. Okay, correlation, as you know, the maximum value will be 1, minimal value will be -1. Okay, so PCA is a technique that was developed by foretelling, right? I just wrote it in my notes, so I spoke it out. And it's the main thing about PCA is to reduce the dimensionality of the data. And the second is to something we call to maintain or preserve. Okay, so if I ask you, these two axes x1 and x2 are orthogonal, do you mean what it means? Do you know what it means? It means they are in a 90-degree angle, right? So they are you cannot linearly combine. You don't do a linear combination between these two features. Okay, so then if you, the new dimension that you try to do, you do okay. So in PCA we try to transform this data to a newer dimension, and why we do that, how we do that, I will look into it later. We'll look into it later. So maintain or preserve the orthogonality. Okay. Now what you need to understand here is that let's come back to I'll draw this diagram here again. So this diagram was like this, right? This is like this. This is x1. This is x2. Okay. The diagram was like this, and also the variance of the data set. I can draw an ellipse that explains the spread of the variance of the data set. I am not very good in drawing, so please pardon me. Okay, but I hope you understand the idea. Let's just remove it for now. Okay, I don't think it's required. Now, again, let's say the idea is, okay, just hear me out, okay? Why we do it, we'll see that later. We'll just hold on for some time. Just hear me out for now, okay? Let's say I rotate these plane theta degree anti-clockwise. Some angle theta, I rotate it anti-clockwise, the axis. Now this x1 will now maybe, okay, come here. Okay, this blue dashed line that I'm drawing is the axis x1 when it is rotated 30 theta degree, sorry, not 30 theta degree anti-clockwise. Let's call it z1. Okay. Similarly, this x2 will also rotate by by theta degree, right? It will, let's say the new axis of z2 is this. Here also theta, right? So this is my z2. Okay, why we did this? Please hold on. As I said, I'll explain. So this is what is done. I just rotate this to axis, this plane, theta degree, anti-clockwise. Okay. Now, if I rotate this data, when I rotate this, if you look at it from the plane of z1, right? Z1 is a new rotated plane theta of x1, right? If you look at the transform. Sorry, yeah. So if you look at this transformation, the axis will now look like this. So Z2 became perpendicular now. That's what I did, the rotation. This is my new axis Z1. This is my new axis Z2. One second, I deleted. This is my, this one, this is my, this one. Okay. And now the data will be like this. Okay. And it will be like this. Okay. Now you might see what is happening here. Again, if you don't, then okay. Now it will do is to explain this. I draw an ellipse that covers all the point of the data set to explain the spread. So the variance of Z1 is this, right? The variance of Z2 is this. Now, can you tell me which data has more variance? Which data has more variance? Can you tell me? variance of Z1. It's clearly visible now, right? So that's the first most important point. The variance of Z1 is more than the variance of Z2. And once the variance of Z1 is more, it means the spread of data that explains what the data is probabilistically is better when you are considering Z1. Z2 is not giving you that much variability in the data, so it will not give you too much information. And if you see, these two axes are orthogonal. Yeah, Z1, Z2 are orthogonal. Again, my drawing is not showing that, but please, sorry, right? So it's orthogonal. Now, the most important point that you have to note here is, okay, the variability across Z1, Z2, sorry, the variability across Z2 is less, okay? So there is not much information contained. So if I want to ask you tomorrow, you want to reduce this set of data to one dimension, I think it's better to just take Z1. Do not take Z2 because it's not giving you that much of information. Okay, now this might also answer one more question of you might have is what does PCA tries to maximize when trying to reduce the dimensionality? PCA tries to maximize. There is a question, okay, in the MCQs that I have planned today. So PCA tries to maximize the variance of the transformed features. Now, how does PCA do this? Is what is the topic of the lecture, right? We are still in the introduction, right? So let's again. This was important to start with in this way. So this is basically what PCA tries to do. It tries to project your data in a different dimension such that the variance is maximized and orthogonality is preserved. Okay. Okay. Any questions before I continue? Okay, no questions. Let's continue then. Okay. Yeah, sorry, I zoned out a bit. Sorry. Yeah. So, okay. Yeah. So basically, what we are trying to do is given Z, right, and Z being M cross one feature vector, we want to reduce it to Z M dash or ZP cross 1, where your value of P is less than or equal to the value of L. Okay, and by losing very little information, again, if you maximize the variance, you lose very less information. Okay. Right. So now let's look at the derivation of PC, and this is where the math begins. So this is the Cartesian plane, okay? And let's say there is a point M here, okay? It has two coordinates x1, x2. Okay, this is my x1, this is my x2. Okay, so I can draw a line from the y-axis, x2 axis, from the x1 axis. This point is called, let's say, m1. This is nothing but x1, 0, and this point here is m2, and this is 0, x2. And this is very high school basic math. Now in PCA we try to rotate this point by some theta, rotate the axis by some theta anti-clockwise. So let's do that. Let's say the new axis is okay, and it's going up as a for the Z2. Okay, this is my Z1, this is my Z2. Okay. Okay, clear? Clear, right? Okay. Now this x1 that we have here, right? Let's focus on m1 first. Okay, let's focus on m1 first. This x1 that we have here on the bottom, we want to project this point on z1. Okay, how do we project is the entire question, but we'll answer that. Okay, similarly, this is the projection of the point m1 on z2. Okay, now this angle is theta. This angle is also theta. This angle is also theta, right? Right, this is I really expect some background on this. I don't want to explain geometry today. Okay, and this angle is theta as well, and this point here m2 falls here on the z2 axis, and it falls here on the z1 axis. Okay, now for people who still remember the trigonometry lectures, right? Now for z1, if I want to find the linear combination of x1 and x2, which is a projection of points m1 and m2 on z1 and z1 axis, how do we do that? So we know that what is the formula of cos theta? I'm just calculating for one. For others also you can do it, but I'm just helping you calculate for one. Cos theta is base by hypotenuse. And focus on this triangle for now, right? This one, this triangle. Okay. Now we know this. We know this. This is the hypotenuse of the, because this is the base, this is the perpendicular, this is the hypotenuse, and this is x1, right? So cos theta equal to base, and what is the base? Base is this, base, perpendicular, hypotenuse. Hope you have not forgotten that, right? So cos theta is base by x1, and so what is the base? is x1 cos theta. Okay, so on z1 for x1 it is for m1 it is x1 cos theta, and if you calculate for m2, which I highly encourage you to pause the video and do it. If you don't, then if you can't do, then please ask in the comments, but I hope you do it. x2 sine theta. Similarly, for use a different color, for z2 it is minus of x1 sine theta plus x2 cosine of theta. Okay. 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 Now we have this. Okay. We can project. We found the new values of z1 and z2, which is the projection of points m1 and m2 on the z1 and z2 axis respectively. We can write this equation in matrix form. We can write this as this is a vector z1, z2. Okay. Is equal to, we can write this like this. Okay. I'll just write it first down and then I will explain you what's happening here. Cosine of theta, sine of theta, minus sine of theta, cosine of theta. And it's multiplied by a vector x1, x2. Okay. Now if you do the multiplication, you will get the equations on the top. Z1 will be equal to x1 cos theta plus x2 sine theta. Z2 will be minus x1 sine theta plus x2 cos theta. Okay. I call this vector Z. It's a m by 1 vector. What is m? Number of features. There were two features x1, x2. We are trying to rotate them and make them z1, z2. So they are still m by 1. This here is a m by m matrix. I call it A transpose. Okay. Okay. And this is the vector x, the feature, right? And this one is m by 1 as well. Okay. So if this is A transpose, then what is A? You take the transpose of the above matrix, you get A. Cos theta, sin theta, minus sin theta, and cos theta. Okay, now this is the last time I'm introducing cos theta and all that. For now, I'll just replace them with generic terms. I call this, so okay, I'll just use some other color. So I call this thing vector x1 or vector a1, and I call these two elements vector a2. Vector a2. Okay, so if I call it that way, then here is my a1, 1. Okay, here is my a1, 2. So a1 has these two components, a1, 1, a1, 2. And this here is called, can you guess, a2, 1. And this one becomes a2, 2. Okay, now this was for number of dimensions m is equal to 2. Now if I consider for m is equal to m, what do we have? If m is equal to m, then I have a m by 1 dimensional z vector. Okay, I will have those vector components here. So it will be a11, a12, so on and so forth, a1m, so on and so forth, am1, so on and so forth, amn. Right? And this vector here features is x1, x2, so on and so forth, xn. So this here becomes very important. Z vector z is equal to a transpose x. This is the most important equation for PCA. Okay. Okay. So now we can project vector x using the vector A. We can transform vector x to vector z. So that is done. Transformation of feature. This is the generic equation. It's done. But I also told you there was another requirement. The other requirement was that you want to actually um, uh, let's go. So you also want the orthogonality to be preserved. And by the example I showed you, right, I took cos theta, sin theta. How is the orthogonality being preserved, right? It's a very normal question, very basic question that a person might have. So if you have the vector A again, if you have, let's say, cosine of theta minus sine of theta, sine of theta, and cosine of theta. Now, can anyone guess what can I do to say this matrix is orthogonal? I can do A transpose A. Very good, very good. And what do I get if I do A transpose A? So I can also do A times A transpose. I should get the value as the identity matrix. And if I get, you'll get, if you do this right, just do this on your own, you'll get I. Okay, it's a very simple matrix multiplication. Come on, I don't want to do this now, right? So you'll get the identity matrix I. Now, if you look at it in a different manner, right? For people who have learned linear algebra, they might be able to answer the nature of the output that we have. The first row contains the dot product of this vector with this vector. Second will be this vector and this vector again. So, given Z1, to get the first equation for the first transformed dimension, it will be Z1 A1 transpose X. Okay, so this is your A1 transpose, right? This thing. This is your A1 transpose, right? Because A1, this is already written as A1 transpose, A transpose, right? So first row is A1 transpose X. Similarly, Z2 is A2 transpose X. So on and so forth. Zm is An transpose X. Okay. And you might now tell me, boss, we are about to do feature reduction. I've not done feature reduction, right? Here is the thing. So this set of vectors that I have written, this set of equations that I have written, typically there are two requirements. First is each AI transpose AI should be 1, so that this is orthogonal. The second important definition, the variance of Z1 should be the maximum, followed by the variance of Z2, followed by the variance of some I, Zi, and then the variance of Zm should be the lowest. Now, depending on the value of I, you might have the value of I as 2. So you will only get Z1 and Z2. You might have the value of I as 3. You'll get the vector Z1, Z2, Z3. It all depends on what is the value of I. That many features or dimensions you can finally extract, and that's what gives you the final reduced dimension. Okay. Now I'll throw a lot of statistics at you. Okay. So let's just take one of the Zi is equal to AI transpose X. Okay. Now, what is the variance of Zi? Can I comment on the variance of Zi? The variance of Zi is nothing but the variance of AI transpose X. And I expect some background and statistics. Again, I'm not going to the basics of variance, how to calculate and all. This is AI transpose the variance of X AI. Okay. Okay. What is the expectation of Zi? Expectation of Zi is nothing but the expected value of AI transpose X. This is nothing but AI transpose expectation of X, expected value of X. Now, you know there are two things, right? There is something called population and there is something called sample. Right? So let's say you know the population variables. So that one is called sigma, right? The variance. It's also called the covariance of X, the covariance matrix of X. So it's the um, sigma, so it's population. Or you might say, I don't know covariance. I know the sample variance, small s. Or you might also, for mu, it is nothing but the expected value of X. If you know the population, it will be mu. Or you may call it X bar if you do not know the mu. So sample mean is called X bar, the expected value of X. Okay. Now, if you know the population parameters, obviously you are very good, right? You have done almost half the job, right? You know the population parameters. Hard to find it, but let's say you know. Then this is called population PCA. There's a name, right? There's a name for it. This is population PCA. If you know the sample estimates, it's called sample PCA. Okay. Now we'll focus on sample PCA because that is what is actually known. So, right, sample PCA is what we'll focus on. Now, sample PCA, right? Again, let me write it again here for your notes. So, expectation of Zi is nothing but the expectation of AI transpose X is nothing but AI transpose expectation of X, which is X bar. Okay. The variance of Zi is nothing but the variance of AI transpose X is nothing but AI transpose small s AI, where your AI is the covariance, sample covariance. Okay. So this is sample PCA. This is the expected value and all, and you will get the individual principal components called Zi by the equation AI transpose X. Okay. And for your notes, uh, uh, each principal component is a linear combination of X. Okay. And so all the principal components form a m by 1 vector. Okay. Second, the first principal component, this is what I wrote earlier as well. So the first principal component is A1 transpose X, I is equal to 1, right? A1 transpose X, subject that to the fact that the axis is orthogonal, which means A1 transpose A1 is 1, and it maximizes the variance of A1 transpose X. Okay, and each subsequent principal component will be arranged in a decreasing order. Okay, I'm not writing it again. Okay, A1 is the component with the highest maximum variance, then A2, then A3, then A4, then so on and so forth. What you need to know here also is that each of these principal components, the covariance between any pair of principal components AI, Aj, such that I is less than j, should be 0. Which means A1 transpose X and A2 transpose X covariance should be 0. A1 transpose X, A2 transpose X, A3 transpose X covariance should be 0. A2 transpose X, A3 transpose X covariance should be 0, and so on and so forth. They should not have any variability among themselves. Okay. So this was about the geometric intuition kind of thing. Now, many people here like to talk about linear algebra, and if you do linear algebra, it simplifies things to a significant extent. And let's go into the fact that how does it try to simplify. So this is from the linear algebra side of things. And if you see, it's very small, okay? Basically, the problem that we are trying to solve here is that given a principal component Zi such that it is nothing but AI transpose X, it maximizes the variance of Zi. Okay, and what is the formula of it? AI transpose sample variance AI, constrained by the fact that, what is the constraint? What is a constraint? What is the nature of AI? It should be orthogonal. So AI transpose AI should be equal to 1. Now, if you were just trying to do maximization, it's a simple maxima minima problem. Many of you here have studied maxima minima, I guess. But here we are not trying to just maximize, we are trying to maximize subject to a constraint. The constraint is that the principal component that you find AI should be orthogonal. So AI transpose AI should be equal to 1. And when you want to do maximization in terms of a constraint, we use something called the Lagrange multiplier. I expect some background, guys. If you don't, please read about Lagrange multiplier. It's a very small, easy concept. Okay, it's just maximization in terms of a constraint. In front of a constraint is Lagrange multiplier. If you want, I can also suggest you some resources, or I can help you to learn if you want to. If you comment or if you share, okay? Not share. Sorry. If you comment and if you are not sure, so constraint-based maximization problems, Lagrange multiplier comes into the picture. Lagrange multiplier is basically a function L. Just before I do that, I'll maybe try to do one more optimization. I'll bring this one on the left and write this as like this, right? Same thing, I just bring this one on the left hand side. Okay. Okay. Now, the Lagrange multiplier, as I said, capital L is a function that looks like this. So what are we trying to maximize? We are trying to maximize AI transpose S of AI. Okay. Minus, what is the constraint? Lambda is the constraint. So lambda, what is it called? I will tell you, is AI transpose AI minus 1. Okay. So lambda is called the Lagrange multiplier. Now, if you want to this is a function, right? I want to maximize this function. So what do I do? Maxima minima rule. You differentiate it with respect to AI and equate it to 0. So I do dl by dai, sorry, and I equate it to 0. So if I differentiate the above equation, I get 2 times, I'll use a different color, right? So 2 times S of AI, okay, minus 2 times lambda of AI. This is equal to 0. Now you might want to simplify here, right? And 2 and 2 maybe cancel out. You can say that way, right? 2 and 2 cancel out. So I can write this as S minus lambda AI is equal to 0. Now there is a problem with this equation. The problem with this equation is, what is the dimensionality of S? The dimensionality of S is, it's an M by M matrix. Lambda is a scalar. Is a scalar. How do I do the subtraction? We can introduce I, the identity matrix, which is a M by M dimension, and now you will be able to subtract. Okay, and AI you might know already by now, I guess it's a M by 1 vector. Okay. Have you ever seen this equation somewhere? If you remember the start of the lecture, I told you a prerequisite. If you still remember, you will be able to answer. So have you seen this equation somewhere? This equation. How many of you here know how to calculate eigenvector? Right? It's the aha moment for people who know eigenvector. You are actually calculating the eigenvalue and eigenvector now. Okay, good. So to calculate this, what you do is you take the determinant of S minus lambda I and you equate it to 0. And this here is called, what is it called? Characteristic equation. Good. How many roots does it have? How many roots does this equation have? M roots. Characteristic equation. It has M roots which denote the different eigenvalues. Right? It has M roots. Which denote the M different eigenvalues. If you find the eigenvalues, you can find the eigenvector. And what do those eigenvectors mean? Those eigenvectors are nothing but the individual principal components. That is the whole funda of PCA. See, it's very easy to derive using algebra. Although you would still had some background of how this came into the picture, but yeah, after that, yeah. Okay. What is your S here? S is your covariance matrix. I'm just giving you a small homework kind of thing for you to practice. Take this as a covariance matrix. Okay, this is one of the covariance matrix. 1.15, 5.76, 5.76, 29.54. It's not correlation matrix, so don't ask me why is it not 1. Okay, it's covariance matrix. And if you find the eigenvalue and then get the eigenvector, your two equations, Z1 and Z2, should be this. Z1 is 0.19 x1 plus 0.98 x2. Z2 will be 0.98 x1 minus 0.19 x2. Okay, your lambda you will get is 30.66. Am I not able to write? Yeah, and lambda 2 is, what the hell, 1 second. Yeah, 0.03. Okay. See, everything just boils down into doing eigen decomposition, right? Eigenvalue decomposition. Okay, any questions? Any questions? No questions? Okay. So this was PCA. Now let's look at some questions given on PCA. And once that is done, then we'll end the class. And tomorrow we'll talk about linear discriminant analysis. Let's solve some questions on PCA, some important questions on PCA. There's one question given in GATE last year also. It's a very basic question. Yeah, don't even call it a PCA question, general knowledge question, but still we have to do it because it was asked. Let it load. Wait for it to load. Doesn't seem to load. For me, it shows a blank screen. We'll wait. Okay, yeah, it can. So dimensionality reduction techniques are used to do what? They are used to do reduce the number of features in the data set. Easy, right? Easy. PCA is a dimensionality reduction technique that there could be more than one option correct. Please take some time. So it maximizes the variance in the original feature, it maximizes the variance of the transform features. What do you think? Option D is correct, not A, okay? Option C is also correct. It creates a new features that are linear combinations of the original feature. PCA finds the directions of maximum variance in the data by doing, come on, I just taught you. It does eigen decomposition. Good, 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 very good. Eigen decomposition. Which dimensional reduction technique is based on linear positions of data on a lower dimensional subspace? This is just other ways of asking what is PCA. So you're trying to reduce by doing linear projections, linear combinations of the data into a lower dimensional subspace. If you have a subspace with m dimensions, you're trying to lower it down into m prime, which is a lower dimensional space. So PCA. The most popularly used dimensional reduction algorithm is PCA, right? Which of the following is or are true about PCA? PCA is an unsupervised method of optimization. Is that true? Yeah, it's true, right? Unsupervised, right? It searches for the directions that data have the largest variance. Come on, that is the whole point of doing PCA, right? You're trying to maximize the variance of the transformed directions. Considering those were transformed, you get the maximum variance. Maximum number of principal components that you get will always be the number of features, and you may reduce it so you'll get less than or equal to the number of features. And obviously that's a requirement of PCA, which is all the principal components are orthogonal to each other, right? So all the statements are correct. This is a very important question for your exam. Okay, this was a question that was asked in GATE 2024. I don't see this is a question of PC only, but still, okay, they have asked. So PCA is dimensionality reduction. So P is 2. That means option A, option D go down. They don't are not true anymore. Huh. Logistic regression is a discriminative model. Naive Bayes is a generative model. Okay, so option B is correct. Why they are generative and discriminative? Please watch the lectures. I've talked about it extensively. Right? Okay, I think it's done. No more. Yeah. So this is all I had to share about PCA, what it does, how it works. Tomorrow's class, next class, we will look at linear discriminant analysis, which is the last topic. If I do that, if I can complete that within 2 hours, might take some more time. Might. Don't know. I don't know how much I will teach you the idea because you should also consider the fact that everything can't go inside your brain in 2 hours. So I'll still try to kind of finish things off and make you understand concepts so that you are able to answer the questions in the exam. That's our whole idea. And also tomorrow we may, if we get time, we'll solve some questions as well. I'll have bring questions. I will still bring questions. If we get some time, we'll solve them. And that will be the end of GATE DA machine learning syllabus. Okay. Again, thank you for joining. If you have any questions, feel free to comment down below or ask your question away. And if it's helpful to you, please also some can also meet. So okay, okay. Anyways, okay. Thank you guys. Thank you for joining. Thank you for listening to this lecture. See you guys tomorrow. All the best for your exam or whatever. Right.